Hello, multivariable calculus students. Today we're going to be finding in this lesson the volume of a tetrahedron with vertices 0, 0, 0, 1, 1, 0, 0, 1, 0, and 0, 1, 1. And we're going to be doing this using triple integrals. Okay, so to start, in this problem we're going to be using this order of integration. And depending on the problem, this may be the easiest order of integration, or another order of integration may be easier. And we want to develop the skill of being able to do different orders of integration. The idea is that some problems will be easiest to do in a certain way, so if you can do it in a variety of ways, it's going to help you solve a lot of problems. Okay, so this tetrahedron, I've already graphed for you down here. Tetrahedron is just a four-sided shape with planes as its sides, right, connecting the points that I've specified up here. Okay, so here it is. I've drawn it in purple on our nice XYZ axis. And we want to set up an integral with this order of integration right here, right, which is the volume of this tetrahedron. Okay. Most people find that it's the setup of the integral that's the toughest for these types of problems. Okay, so here we go. Triple integrals, so of course we have three integrals. The problem said do it in dz, dy, dx order of integration. Okay. Now the first thing I look at here is the fact that the innermost integral is z. Okay, so this orients us. This says pretend you're looking down the z-axis. Look down the z-axis. What shape is made by that solid in the xy plane if you're looking straight down? You can imagine this as, okay, suppose that there's a bright light behind me, way above me on the z-axis, and I'm looking down. What shadow do I see? This is a solid. Let's assume it's a solid light blocking object. So it's going to make some kind of shadow in the xy plane. What is that shadow? That shadow is going to tell us the region of integration for the outer two integrals. That's a region we usually denote with R. The region that we're integrating over, namely this tetrahedron, we're usually going to call that D. Okay? Now, let's see what that shadow is. Let's look at this nice little set of axes over here. Y and X. Let's try to see if we can figure out what that shadow is in the xy plane that this solid is making. In this case, this is really nice and easy because this solid, this tetrahedron, is right on the xy plane. So that shadow is this shape right here. Okay. Over here, if I draw that region, this is going to be our region R. You can see we have a line which goes from the origin to the point 1, 1, 0, which in the xy plane, of course, is just the point 1, 1. We have this line over here, which is the line y equals 1 in the xy plane. So I'm going to draw that over here. Here we go. There's the line y equals 1. This is our region R, right there. That's the shadow that this block, this tetrahedron, is making in the xy plane. And that's going to define the bounds for our outer two integrals, just like when we did double integrals. The fact that x is outside here tells us that what we want to do is make vertical stripes in this two-dimensional region. Looks like x is going to 1. Y, of course, is also going to 1. So I think we're ready to put in our bounds for r. Erase this r so it doesn't confuse us. Okay. X is going to go, right from over here, it's going to go from 0 to 1. Okay, so I can put that in right here. For any given x value, such as the one that this vertical stripe is at, y goes from this line up to this number 1. Now this line is the line y equals x. Right? So that is going to tell me what my bounds are. My bounds are going to be for the y variable, my bounds are going to be from x to 1. So we just did the bounds for our region R, that's the shadow of this tetrahedron in the xy plane. The last thing we need to do this integral is what are the bounds for the z integral. Typically what people do for that is they imagine a ray going from the xy plane through the surface, just like I'm drawing right here. You have to imagine that this ray starts out here, it goes through the solid and then comes out. If you can't quite visualize that, I'm going to erase this ray so that it looks a little more three-dimensional. This dot is where it starts. And I'll put some dashed lines there. There we go. So the first dot right here is where the ray starts in the solid. It goes through the solid, and here's where it exits the solid. This first dot, whatever the z is there, that's the lower z bound. The second dot, where the ray exits the solid, that's the upper z bound. Okay, the lower z bound is really easy in this case. It's just 0. Because that's where this ray hits the solid. It's right at the bottom. Where does it leave the solid? It leaves the solid on this surface, which is this kind of tilted portion of a plane. Okay, so how do we figure out the z value on the surface? It depends on the x and y coordinates, right? If we're over here, if I draw a ray over here, the exit dot of that ray is going to be different than what it is for this dot. So in general, that z value is going to depend on this particular x and y coordinate at this lower dot. Basically, we have to determine the equation of this plane. Now that's a whole other problem, and I don't really want to do that, but you should know how to do that since you're a multivariable calculus student. If I give you 3 points, the origin, this point 0, 1, 1, and this point 1, 1, 0, you should be able to calculate the equation of that plane. At this point, I'm just going to give you that equation, and it turns out to be z is equal to y minus x. That's the equation of this plane right there. The surface is given by this equation, and lo and behold, that gives us the upper bound for z. It's going to be y minus x. That's it. All that work was to set up this integral. And as you do more of these, you'll get much faster at doing it. There's a process. My process was to figure out that R region, which is defined by these two integrals right here. I had to draw this little graph to help me, but you might not have to do that after some practice. And then finally we had to find out what the z bounds were by drawing a nice little ray from the R region vertically parallel to the z-axis through the solid. At this point, we can finally actually solve the problem by doing this integral. That's going to give us the volume of this region, which I call D. Okay, let's do it. Most people find this is, for integrals like this is the easy part. Okay, so we go inside out. Let's do that inner integral first. The integral of dz is just z, evaluated at the upper and lower bounds. So it's just going to be y minus x minus 0, I'm not going to put in the minus 0. We've already got our triple integral down into a double integral. Okay, let's do the inner integral with respect to y. I don't need that integral sign. Integrating with respect to y, I'm going to get y squared over 2 minus xy. And I have to evaluate that from with an upper bound of 1 and a lower bound of x, and we still have our x integral there. I'm going to plug in 1. I'm going to plug in 1 for y and then plug in x for y, and I'm going to subtract those two things. Here we go. 1/2 minus x minus, plugging in x now, x squared over 2 minus x squared dx. At this point, we've got an integral like you would have seen in single variable calculus. I think I'll simplify first. 1/2 minus x. X squared over 2 minus x squared is minus x squared over 2. So we get an extra. Okay. Continuing to do the integral, I get x over 2 minus x squared over 2 plus x cubed over 6, evaluated upper bound of 1, lower bound of 0. If I plug in 0, I'm just going to get 0. So all I have to really do is worry here about what happens when I plug in 1, which is 1/2 minus 1/2 plus 1 over 6. And finally, after all that work, I get the volume of the tetrahedron is actually 1 over 6. So this tetrahedron has a volume of 1 over 6. The hard part, I think, for most people is building this integral. Once you've gotten that, the rest of it is algebra that you should know from calculus and some arithmetic, which you should know from a lot long ago than that. And her answer was 1/6. Okay, now we're actually done with that problem. Again, I said it's a good idea for us to try to get practice doing the same thing with a different order of integration. In this case, here's exactly the same problem, but now we're going to do it in dx, dy, dz order. That may or may not be easier, I don't know, until I actually do it. Here we go. Same kind of setup as before. There's my three integrals, dx, dy, dz. Okay, again, the thing to note first, what's on the inside? What's the innermost integral? It's the x. Okay, so to figure out the region R, which is what defines the bounds for these two integrals, I imagine I'm standing somewhere on the x-axis and I'm looking back toward the origin. Maybe there's a bright light behind me or whatever it is, but whatever it is I see in the YZ plane, that's the shadow, that's going to define the region R that I talked about, which defines the bounds for these two integrals. So let's go over here to my axes, which now I'm going to label with Y and Z. This is going to define our region R. Now if you look at this, you realize, okay, this solid, it's right up against the YZ plane. The shadow is just being formed by this triangle that I'm outlining right here. That's going to give us our region R. So if I draw it over here in the YZ plane, we've got this nice straight line there. I should really make a straight line. Don't want to get too sloppy. Okay, there's a nice straight line. Nice vertical line there, okay. This is the point in the YZ plane. This is the point 1, 1. We're just forgetting about x at this point. It's just 0. And of course, this is 1, 0. Therefore, this is the line z equals y. And this is our region R. It's our shadow region R. Now notice the order of integration. Z is on the outside, Y is on the inside. That tells us that the person who designed this problem wanted us to do horizontal stripes here. Let me draw a little horizontal stripe. There it is. Okay, so outermost, Z. Z goes from here to here, which you can see is just 0 to 1. That makes our Z bounds nice and easy, 0 to 1. So I just put those in there, 0 to 1. For a given Z value, Y goes from this side, along this stripe, it goes from this point to this point. So it's going from, Y is going from Z along this line, right, to the value 1. So there's my Y bounds, Z to 1. So we just finished the region R. That's what these two integrals do for us. Now we need the X integral bounds, and this is where our ray comes in. We imagine a ray, in this case going from the YZ plane parallel to the x-axis through the solid. Let's see if I can draw that. This isn't always easy in a three-dimensional thing, but let's see if I can do it. So here we are. I'll try to make it parallel to the x-axis. There we go. A little arrow in there. And I'll try to erase some things because this thing is actually going through the solid. And I'll draw this dot even though you really can't see that dot in principle because it's behind the solid. But okay, and this dot is where it comes out. So the first dot tells us our lower x bound. The upper dot, or the dot which is farther along the x-axis, shows us our upper x bound. Well, x starts at 0. That's what that dot is. So I'm just going to put 0 on my integral. This dot tells me the biggest value of x along this ray. How do I get that? Well, I know my equation of the plane. Solve this for x. That's going to tell me my biggest value of x, which you can see x is just going to be y minus z. That's what goes right here at my upper bound. So I'll just fill that in right here. There it is. That is our x integral. By x integral, I mean x was on the inside and our R region, our shadow region, was in the YZ plane. And you would have to verify this. I mean, if you didn't know, you don't know if this is right or not, right? But if we go through this and integrate this, you'll find that we actually do get 1/6. It shouldn't matter because we got 1/6 before. It should not matter what integration order you do things in. You should get the same answer. It's just that some integration orders will be easier to do, either to set up or they'll be easier to evaluate than other orders of integration. But this is the volume of the tetrahedron using this order of integration. And if you want, for extra practice, you can verify that when you integrate this particular integral, you still get 1/6. Let's try one more way to integrate to do the same problem. It's kind of overkill. We're doing the same problem 3 times. Now we're going to use dy, dz, dx order of integration, which is probably, I think for this problem, is probably the toughest one. But it's really not that much harder. We're going to use the same process as we did the other two orders of integration. For Cartesian coordinates triple integrals, there are 6 possible orders of integration. There are 3 possible ways for the innermost, 2 possibilities for the middle, and then only 1 possibility. Multiplying those things, you get 6 possible orders. We're only going to do 3 today. I think that's good enough. So here we go. Triple integral dy, dz, dx. Once again, I focus what is on the innermost integral. It is y. So we have to imagine that we're sitting far along the y-axis, looking back toward the origin, what do we see? What shape do we see? All we see is this solid. We can't see this side. All we see is this side, right? If there was a light behind me, this side is the thing that would create the shadow back here on the xz plane. So our region is going to be in the xz plane. I'm going to draw that. You don't have to do this, but it's kind of nice. I can also draw it right on the diagram here, what I'm going to get. We can do both things. So here we go. The shadow of this guy, this is a nice little triangle. It's going to make a nice little triangle right in the xz plane, right as I'm outlining right here. I'll draw it right now. If you can see that triangle, there's my region R. If I put that over here in the xz plane, where we don't have to worry about 3 dimensions and so forth, it's going to look something like this. I think you guys probably get the idea at this point. This is 1, 0. This point is 0, 1. This is our region R. If I look at my order of integration here, this says that we're doing, at least in this diagram here, we are doing vertical stripes. Oops. Nicer to have a vertical line there, so it looks a little nicer. There we go. Okay, so x goes from 0 to 1, so I'll just put that in my interval, 0 to 1. For a given value of x, which is where this stripe is, z goes from 0 to whatever this line is. What is the equation of this line in terms of z? That's not too hard. This is just z is equal to 1 minus x. So that becomes, for our z bounds, which is what we're looking for, z goes from 0 to 1 minus x. So let's put that in the interval, 0, 1 minus x. Okay, those two integrals define our region R. Now we're ready for our final integral on the inside, and that we need to use our little ray. I'm going to try to draw a ray again. Now we have to go back to the 3-dimensional diagram here. Okay, so I pick a point in the R, and I draw my ray. Here we go. A little arrow on it. Okay, so here we go. The ray enters around here. Let me erase the part where it enters to make this a little 3-dimensional looking. And I'll put dots. Here's where the ray enters. Here's where the ray exits. So this dot on the left here at the lowest value of y is going to give me my lowest bound for the y integral. This upper dot, where the ray exits the solid, is going to give me my upper y bound. The upper y bound is actually the easiest in this case, right? The y value is simply 1. So I'm just going to put a 1. Right? That bound is 1. The lower bound is a little trickier. Right? It depends on what x and z are. Well, we know the equation of this plane. I solve that for y, and I'm just going to get x plus z. There it is. There's our integral done in dy, dz, dx order. Again, for practice, you can do this out and verify that you're going to get exactly the same value that we got for the volume, which should not depend, the volume of this thing should not depend on what order of integral we do. Okay, that would be bad. But it's good practice to know how to do different orders of integration so that when we do get problems where one way is harder than another, you'll be able to do you'll be able to do the easiest order of integration for that particular problem. Okay, that's the end of this lesson.